In part 3, we repaired an old cabinet that we can use to test our retro build. During that repair, we temporarily jumpered up enough controls to run the board on the bench. In the project plan, we said we'd build a control board first, so we can use it for both breadboarding and testing. In this video, we'll design that board. First thing is to figure out what parts we'll need. I used information from the schematics, board, and harness to create this diagram. First, we'll need the proper 44-pin card edge connector. The spacing is 0.156 inches, which makes no sense and doesn't even have an integer per inch count. But if you convert it to metric, it still doesn't make sense. Someone let me know why they made this particular spacing. There has to be a reasonable explanation. Hopefully not drug-induced. Now the solder tail versions of these are the cheapest, so we should add surface pads that you can solder these to. The clearance is wider than the board, but you can sacrifice yourself and bend some pins for the lower cost. We will also add pads for through-hole versions, so you'll be able to use straight or 90-degree pins for vertical or horizontal orientation. Let's also add a single row header so we can easily stick this into a breadboard. On our retro version, we'll add a matching header so you don't have to buy the 44-pin connector. I guess we'll start at the top. We'll need power, and we don't need a 16.5 volt center tapped AC transformer. We can simply supply 12 volts DC to pins 3, 4, Charlie, and Dog. So let's add a 2.1mm jack so we can plug in a 12 volt DC switching brick. It'll need to be at least 3 amps for legacy boards. I think we should also add a power switch so you don't have to remove the DC plug to turn it off and on. And you can jumper that out if you don't want it. Let's add LEDs for both the 12 volt and 5 volt supply lines. Next, we've got these two incandescent bulbs. Since the SCRs drive these two outputs to ground, we can replace these with LEDs. Just hook the LED anodes to the outputs and the cathodes to 5 volts through 1K resistors. For the serve LEDs, we only need to hook up the upright cabinet signal from pin Peter. Both pins Peter and Jack come off the same logic output, but since the cocktail table has 2 LEDs in series, they half the resistance to pin Jack to double the current. We'll add another 1K resistor in series on this board because 300 ohms is still way too low for today's LEDs. For the coin inputs, we'll use 2-pole momentary switches. This is where the money is, so Atari is a tad persnickety about sequencing the switch logic. You'll only need to really populate one, but for the empty site you'll need to tie the normally connected side to ground. For the start game inputs, we'll use simple push buttons. We have no use for the coin counter signal, but we can at least bring it out to the strip header. You know what? We might as well drop an LED on that line so we can visualize coin drops. I'm assuming the signal is wide enough to see, because it has to be wide enough to drive a mechanical thingy. For the paddles, we'll add both pots so you can run as player 2 in cocktail mode. You don't have to populate the second one, but we'll include a sight. Let's drop an RCA connector for video, and we'll also bring pin Whiskey to another RCA connector for audio. We'll route this on the retro board, and you can tack a cap on the legacy boards to bring out the signal. This line can then be easily connected to a monitor or amplifier. We only need one serve push button. It is interesting that the buttons are hooked in parallel on the cocktail table model. You can basically start the other player's game. It's another difficulty feature. For the speaker signal, we'll add a quick connect terminal. I think that's about it. Oh, for the antenna signal, we'll go over this circuit later, but they have pin 17 hooked to the base of transistor Q2 to detect static spikes and reset the game. This prevents prospectors from trying to shock up coin credits. we can abuse this line for purposeful resets. So we'll add a push button switch and a 47K resistor to plus 5 volts, just enough to tickle the base and cause a reset. I said in the first video that this is an AutoCAD Eagle shop, but to make this accessible to more hobbyists, I'm going to use KiCad instead. Now, I've never used KiCad before, so this should be interesting. I installed version 8 and read a few docs. I think the philosophy is going to be the same. Put all parts we'll use into our own libraries, so everything is narrowly corralled and easier to share. I have no clue what the community conventions are, so I need to learn as I go. And this is not going to be a KiCad tutorial. I'm the one that needs the tutorials. So I'm going to do a lot of the control board design offline so we don't waste time and I don't embarrass myself too much while trying to familiarize myself with this tool. I'll show more of the design work when we do the retro board, as that's the main focus of this project. First, we'll create a breakout symbol library. And our first symbol will be the 44-pin connector. We'll make all pins passive so we can use it for both the control board and retro board. Otherwise, we'd need to make two different symbols depending on the signal direction. I'm not generally a fan of making the symbol match the physical footprint layout. I like a more logical layout, but for this connector, it makes the most sense. Let's also make a SIP header version. We need a single row strip header so we can use this for breadboarding. You can't stick a 2-row header into a breadboard unless the pin usage is the same for both rows, which is something we could do if we needed more current. We'll copy power pins from one side and all used signal pins. Looks like we need at least 25 pins. Let's keep it at 25 so you can use a 50-pin ribbon cable to separate the boards if you want. I'm going to steal some of the other symbols and copy them into our library. We'll borrow more as we go. Let's also create our own footprint library. And once again, the first thing we'll add is the 44-pin connector. We'll do this based on the manufacturer's datasheet and their recommended layout. Our footprint's going to be a bit different because we want to accommodate 3 different parts. A straight through-hole version for vertical orientation of the control board, a right angle through-hole version for horizontal orientation, and a pad version that you can solder eyelet-type connectors to. For physical strength, I like to make the pads as large as possible while allowing a nominal 12mm trace with proper clearance between the pads. If we can't find suitable footprints in the standard libraries or free ones from the manufacturers, we'll roll our own. I made footprints for the mini toggle switches and potentiometers. I'm designing for the Bourne's PDB 181 series pots with a K-style footprint. These are low cost and in stock at most suppliers. The pots will go in from the back side of the board, so the D-style footprint would be perfect, but they're harder to find and more expensive. We'll just get the K-style and bend the leads. I mirrored the pads so we can mount these as needed to match paddle motion depending on board orientation. I couldn't find free 3D models for the pot, 44-pin connector, or mini toggles, so I rolled my own in Fusion. Export them as step, and set them up as 3D models in the footprint editor. I created a control project and created this schematic with all the required symbols. I then created a PCB from that schematic, arranged the parts, and routed the traces. We'll put the ground plane on the back side and use the front side for 5 volts. I created a zone for the 12-volt feed on the top side. I also added a few large vias to add extra beef to the DC jack ground line. I really like this built-in 3D viewer. For manufacturing, you run the fab stuff to produce Gerbers and drill files. I use JLC PCB, and you just need to adjust the settings per their KiCad specs. Always a good idea to open the fab files in a Gerber viewer. The built-in one is pretty good. Should check each layer individually and even do some composites. I find it a good idea to print out the holes and silkscreen layers. I wish they had a multi-layer setting instead of printing one layer on each sheet. Found that out the hard way. I'll use this sheet and physically stick in one part of each footprint as a sanity check. Seems low-tech, but I've fixed a few cases of the dumbass this way. When you're ready, you zip up the fab files. These already have the preferred JLC PCB extensions, and drop them onto the website. It only takes a few seconds. You should do a quick sanity check with their 2D and 3D viewers after uploading. They also have their own DFM checker. You can easily see what they are looking for and try to design to keep all of these green. We can see where they bitch about the connector fingers being too close to the edge. This is intentional, so these are okay. You can also see some minor things like the default KiCad silkscreen line width is a bit too narrow. We'll change this for the next time. When ordering, there are lots of options, but for this board we'll keep all defaults. Super simple, 5 boards for $8. Can't beat that. Even the shipping costs more. 30 years ago, we would have paid $1,000 just for the fab setup for any board. The low cost reduces fears of making mistakes. While not fun, mistakes at least won't break the bank. I'm cheap, so I usually take the lowest price shipping. Boards take a maximum of 2 days to make. For me, boards show up on average in 13 days when I use the cheap shipping. Naturally, you can get stuff a lot faster at a higher cost. On the website, you can watch the production status. Well underway in just a few hours. While we're waiting for those control boards, we've got some time to make our breadboard. We want to breadboard the entire breakout game, so this is going to be huge. I'm using a mix of BB630s and 830s from Busboard Systems, so we get the correct number of power rails. We only need 1 power rail between each board. We can comfortably fit 6 chips on a board, and if we arrange the chips in the same direction as the chips on the legacy breakout boards, we would need a 2x12 matrix. But if we do them sideways, we'll only need 2x9. We'll actually make it 2x10 so we can accommodate the miscellaneous parts near the connector. One of the biggest pains with breadboarding is power distribution. I created these boards to make it easier. They've got 6-pin headers for the breadboards and pads down the middle for power input rails. They also have sites for filter capacitors. JLC has a great panelization feature. You simply upload a single board design, then tell JLC how you want them panelized. The minimum panel size is 7 by 7 centimeters, and the minimum individual board size is 1.5 by 1.5 centimeters. They will allow smaller boards for an extra setup fee, which I was too cheap to pay. Big mistake. Super pain to separate these by hand. We'll need 11 of these. I picked up this large piece of single-sided FR4 for a ground plane. I also picked up this kitchen cutting board. We'll glue the FR4 to the cutting board using spray adhesive. We'll just expose the edges of the breadboard sticky tape so we can easily pull these off later if we want to reuse them. We'll put down one side, then use the power distribution boards to properly space the other side. Let's put in the rest of the power boards. We'll add a barrel connector for a 5-volt brick. I made up a bunch of jumpers to hold the power rails down. We'll run wire down the middle. For about 3 amps, we'll need at least 18 gauge. I think it'll be easier to use solid, but I don't have any solid 18. Should we? Way overkill, but I don't feel like buying any more wire. I prepared this set. Let's tie them down with jumpers and solder everything down. Looks nice. I also soldered the FR4 to ground and added the barrel connector. Do a quick sanity check. No smoke. That's going to be a great breadboard. Those control boards just arrived, so let's see how they look and throw one together. We'll go from short to tall, so we'll start with the resistors. Push buttons are next. These are just common 6mm tactile buttons. LEDs are next, and naturally you can use what color you want. I'll do green for the credit indicators. Coin 1 plus means you have at least 1 credit and can start a 1-player game. Coin 2 plus means you have at least 2 credits and can start either a 1-player or 2-player game. I'm doing red for both power rails. I'll do blue for the serve switch and yellow for the coin drop indicator. We'll do the connectors next. I'll use this right angle connector. These are about $8 at DigiKey. You can also use a straight pin version if you want to mount the board vertically. You just have to solder all the parts from the back side. You can also use an eyelet version and solder them to the fingers we included in the footprint. Audio and video jacks. And a barrel jack for 12 volts DC. Let's do the mini toggles next and start with the power switch. You can jumper the power switch if you don't want to install one. Wow, I made these holes way too big. Perhaps I was looking at the eyelet spec. I'll put a momentary on toggle for coin 1. If you only use one coin switch, then you need to jumper the unused, normally connected side to ground. For the second coin switch, I used a regular toggle. I didn't have another momentary one. I'll just need to manually toggle back and forth to drop a coin. Pots are next. The left one is for both players on an upright model, and just for player 1 on a cocktail table. I figured out the proper pot orientation for nominal play action with a horizontal control board. Pins on both pots go in the right holes when looking at the face. Right pot is for player 2 on a cocktail table. You don't need to populate it unless you want to test player 2 cocktail logic. We'll solder that 25-pin SIP header from the back so we can use this in our breadboard. Flux wash with iso alcohol and a light scrub. Looks pretty good. I've got this Rev C board handy. Pop that on. Hook up video and audio. I don't have a little speaker, so we'll just jumper the audio bus to pin whiskey. Plug in a 12-volt brick, fire in a hole. No smoke? That's always a good sign. And drop a couple coins. Hey, that coin drop LED works. Looks like it's just on for as long as the coin switch is toggled. Let's start a 2-player game and serve. The left pot works. The second player pot works as well. Let's try out that reset switch. Looks like that's working fine. This is going to be way easier to use and a lot better than all those wires. I think that's enough for today. In GitHub, I added the retro folder, a KiCad subfolder, and a control folder under that with the control board project files. I also saved a PDF copy of the control board schematic in case you just want to look at that. Under Control is a fab folder with this zip file that contains all the Gerbers and drill data. You can chuck this at your favorite board house to get some of these made. Under KiCad, I also added the Libraries folder, which contains our breakout symbols and footprints. Under Libraries, I also added this 3D Models folder, and dropped in stuff I created in Fusion. If you actually use the KiCad files, you'll need to relink these models in the footprint editor. I didn't have these at the same relative locations. In the root of the retro folder, I dropped in a PDF copy of that 44-pin connector diagram. Page 2 has our 25-pin version for use in breadboarding. Well, we're finally ready to actually start looking at the breakout circuitry in detail. There's a lot, so it'll take a few sessions. In the next video, we'll breadboard at least enough stuff to get something on the screen. Thanks for watching.